Privacy filters for displays are designed to hide visual content from unintended users, while making the displayed information visible only to selected viewers. However, existing privacy filters suffer from a wide viewing field, with the maximum viewing angle ranging from ± 30 to 45 degrees, leaving room for potential compromise of privacy. This limitation comes from the trade-off between privacy and usability. While it is feasible to create privacy filter with narrower viewing angles, it would confine the user to a limited range of positions, diminishing overall usability and user experience. One solution to this trade-off is to track the user and provide a narrow, steerable viewing field centered around the user. This requires real-time modulation of the light field emitted by the display. A commonly used, cost-effective implementation of such a light field display is via parallax barriers or lenticular lenses, which have been used in commercial 3D displays such as Nintendo New 3DS and Asus Spatial Vision laptops. While these technologies can deliver the correct view to the user, they also simultaneously exhibit repeated views outside the intended viewing field, compromising selectivity and privacy preservation. We propose a privacy-enabled parallax display, which achieves high levels of selectivity such that only the tracked user can access the correct view. Unlike existing privacy filters, it further restricts the vertical viewing angle, preventing shoulder surfing. So, how does our method work? First, let's use this top view illustration to review how a conventional parallax barrier works. The key idea is to place a barrier with equidistantly placed slits in front of the display. These slits are so small that each eye perceives only one display pixel through them. As a result, distinct images are directed to each eye, thereby generating a sense of depth through parallax. It is important to note that the assignment of pixels to each eye does not have to remain static. By integrating a parallax barrier with a user tracking camera, we can dynamically adjust which pixels are visible to each eye. This capability means that as the user's viewpoint changes, the system continuously delivers the 3D view, ensuring a smooth and high-resolution viewing experience. However, the periodicity of the barrier pattern causes a repetition of views. When a user moves horizontally by a multiple of the period, they can once again see the intended views. This repetition can expose confidential information to bystanders viewing from certain angles. To eliminate the repetition of views, it is essential to disrupt the periodicity of the slits. Our approach involves replacing the fixed distance slit pattern with a randomized slit pattern. In this configuration, the distances between neighboring slits are randomly selected within a predefined range, from S-min to S-max. As illustrated in the figure, this method continues to direct different pixels to each eye at the cost of leaving some pixels unused. When a bystander views the display from an alternate position, the non-periodic nature of the slits alters the interaction of light rays with the display pixels. Since the slits are no longer periodically aligned, light rays from the left eye might intersect with left, right, or even unused pixels. Consequently, the bystander perceives a scrambled image, a randomized blend of the left image, the right image, and black, unused pixels. Here, we demonstrate this idea through simulation results. With the periodic slit pattern displayed on the left, the user perceives a perfect view. However, a bystander may also see the exact same image from certain positions, demonstrating a limitation of this approach in maintaining privacy. Now, let's replace the periodic slit pattern with a random pattern. With this configuration, the user continues to enjoy a clear view, while the bystander perceives only a scrambled image. A significant portion of the image is missing or distorted, rendering it unrecognizable and thereby enhancing privacy. It's important to note that the barrier pattern is not limited to slits. We further introduce randomized 2D pinhole patterns. This approach breaks the slits into a collection of pinholes arranged randomly across each row. Specifically, we independently randomize the column indices of the pinholes in every row. This configuration not only obscures images when viewed from the sides, but also effectively obfuscates views from above or below the user, thereby preventing shoulder surfing and enhancing privacy from multiple angles. While some rough outlines of the image might still be visible, the high-frequency details are completely scrambled. Note that sensitive information are usually found in these high-frequency details, such as text or codes. This scrambling effectively ensures that sensitive information is protected from unauthorized observation. One specific detail to consider is the variation in distance between neighboring slits across the viewing field. This variation can lead to an unnatural viewing experience for the intended users, such as spatially varying brightness and effective resolution throughout the image. To overcome this challenge, we adopt time multiplexing. After creating the initial barrier pattern, we shift it horizontally by 1 pixel at each time interval, producing multiple patterns. If the parallax barrier is implemented with a programmable spatial light modulator, it can cycle through these patterns at very high speeds in sync with the display. The human eyes naturally average these rapid subframes, effectively forming a complete frame that provides a seamless viewing experience. Following previous works on light field displays, we build our hardware prototype by stacking 2 commercial LCD panels rigidly. The front panel modulates light and acts as a parallax barrier, and the back panel displays the content image. By switching the barrier patterns and display images at 240 Hz and a time multiplexing factor of 8, a display rate of 30 FPS is achieved. Please see the paper for more details about the algorithm and hardware implementation. Now let's look at some results. We place a camera on a horizontal translation stage to capture different images observed at different locations. In this experiment, the user is assumed to stand at the center of the display, and the camera starts capturing at 18 degrees from the center. The camera first observes an obfuscated view where the text cannot be recognized. At the end, the camera stops at the user location, where a clear image can be observed. To quantitatively assess performance, we utilize widely used open-source OCR software to analyze each captured image. We then compare the similarity between the detected text and the ground truth text. With the conventional parallax barrier, the display becomes completely black at 6 degrees. However, the image reappears at 12 degrees, allowing repeated views visible to bystanders. In contrast, with our proposed private parallax barrier, the similarity ratio notably drops at 8 degrees. While some individual letters may still be recognized, neither the OCR algorithm nor a human bystander can easily discern complete words. Importantly, unlike the conventional parallax barrier, the image quality in our proposed method does not recover to a recognizable level as the viewing angle increases, demonstrating the enhanced privacy-preserving capability of our approach. In addition to obscuring text, the scrambling of high-frequency information effectively obfuscates other content, such as QR codes. With the conventional parallax barrier, the success ratio for decoding QR codes increases again at 12 degrees due to repeated views. In contrast, with our proposed private parallax barrier, the success ratio remains low for viewing angles greater than 4 degrees. This ensures that bystanders are unable to scan sensitive QR codes, such as those used for friending or payment. In addition to structured scenes like text, here we show an image of a general scene. Although the overall image structure can still be seen at the bystander's positions, details like the text on the banner can only be seen at the user's position, which we claim is the most important information for privacy screens. Here we show another example. Notice the portraits can only be seen clearly at the user's location. One limitation of our current hardware prototype is the extreme thinness of the 2 LCDs, making them prone to warping. Consequently, the displayed images may contain artifacts resulting from alignment and calibration errors, which can degrade image quality even for the intended user. It is important to note that this issue stems from the hardware prototype itself, not from the proposed method. With more advanced manufacturing and assembly techniques, these challenges are likely to be resolved. In summary, we have developed a novel privacy-enabled parallax display that offers a steerable, narrow viewing field to the user. This capability is achieved through a randomized pinhole pattern, which effectively obfuscates the bystander's view while maintaining high image quality for the user with minimal computational overhead. Our experiments demonstrate that, with this approach, image details remain unrecognizable to bystanders. We envision this technology functioning as an add-on to existing parallax displays, providing a more private viewing experience in public spaces.